So I'm here representing Building Futures, which is one of the 8 areas of advance at Chalmers. And this area of advance is about the built environment. So it's about houses and buildings, roads, infrastructures, use of resources, environmental impact, and so on. So this is the group, and I'm leading this profile called Virtual Cities, and that's about using technology and in particular ICT within applications for the built environment. So we'll talk a bit about that. And so how does this technology work? Does it work? Okay, good. So some key challenges. So we as humans face many challenges. 2 of them are certainly urbanization and migration. So more people are moving into the cities. They become bigger, larger, more important, more connected, and so on. So you could make the argument that if you want to build a car or an airplane, you would first simulate the car or the airplane. You wouldn't build an airplane and then see, does it fly? And the argument is that you should do the same thing when you build a city. So you should simulate all the aspects of the city, like the flow of people, the flow of cars, transports, use of energy, resources. Do you have any does the traffic flow work all right? Do you have good wind conditions, transport of heat, and so on? So what we want to do in this profile is to actually build this model. So we want to build this full-scale model of a city containing all different aspects that you can simulate in a city. And then you can provide this to decision makers and architects to provide them with a tool where they can in real time experiment. What if we do this? We move the bridge from here to here. Does that change the traffic flow? Does it affect anything else in the city? So we want to take this as far as possible to build a virtual city in order to provide good tools for planning. So the technologies that we use are, from my perspective, I'm up in this left triangle here, optimization and simulations. I work with simulations. I'm a mathematician, so I'll solve PDEs for a living. But we try to collaborate with research from Chalmers within all these areas to attack these problems in the built environment. So I will just spend a few minutes now to present some examples of work that we're doing within this profile. So let's instead look at some pictures. So this is a picture from one of my students, Carl Lundholm, and he's trying out here a new technology for simulating PDs and doing that on a so-called multi-mesh setting, where we have not only one mesh discretizing the space surrounding these houses for doing this flow simulation, but having multiple meshes. So this provides a very good way to make simulations where you want to move stuff around and have dynamic simulations. So we can work with multiple meshes. This leads to very interesting problems in computational geometry. And when we solve these equations, so we talk about automation. So this is the equation, the Navier-Stokes equations that we solve in order to compute this flow field. And so this is the input, the equation, and this is the output. Another equation that we solve is this one here. This is not something that I might say affects the decision planning for a city. This is the Einstein equations describing, for example, galaxies, but the principle is the same. You have this equation, you write a solver for these equations, and then you get some solution, like a flow field or a galaxy or something else. And the idea we have to automate this is that we built a system where we can write down the mathematics in mathematical form, and then we generate these programs that solve the equations. So typically you have an equation like this one, and you write it down, and then you spend 5 years writing 100,000 lines of C++ or Fortran, and then you run the solver for 2 weeks, and then you get this nice picture here. But our idea is to instead write a system where you can write down the equation, put in the data, and then you generate the code for solving the equation. So this is actual code, a piece of code that we generate for solving some particular equation. So this is automated. We can then attack many different models because you just write down the model, here's a new model, and you press the button, you get the code for simulating that model. So this is one aspect of this work. Here's another example. This is from the Fraunhofer Chalmers Center, they are involved in this profile, and this is not a picture of Chalmers. This is actually a point cloud representation of the geometry of Chalmers. So this is very easy to get. You put out a scanner, and you can easily scan the environment, and you get the geometry of, for example, Chalmers or a city like Gothenburg. You feed this into the simulation, and you can do stuff like this. So we did a wind simulation over the campus of Chalmers, and you can then incorporate the geometry of actual leaves in the trees at this very moment at Chalmers. So this is one of the strengths with this technology, that it's very cheap. You get this geometry quickly, and you just feed this into the solver. And another thing that we're working on, this is my last example. So another thing we're working on is putting all of these tools into the virtual or augmented world. So we do a lot of work now with the Microsoft HoloLens. You put this on, you go around in a building, and you can see through walls what's inside this wall. You see the pipes, you see the wirings, and you bring in the simulation. So maybe you want to simulate how does the ventilation system transport air through the building. What if there is a pollution somewhere? How does that spread through the building? And actually walk around and see and touch the simulation and do real-time visualization and simulation. So this is a very fun project that we just started. So hopefully we can present some nice results later this year. So I will stop there.